The equations below all define the same polynomial function f of x. So they just written f of x in different ways. Here they fully factored f of x out as negative 4 times x minus 3 times x minus 2 times x plus 1 times x plus 5. Then here, this is actually, well, it looks like they factored it once, and then they factored into two quadratics, and then they completed the square for each of those quadratics. And then here, this is just factoring it into two quadratic expressions. And then here, this is the thing just fully expanded out, multiplied out as a polynomial. Which form of f of x is most useful for determining end behavior? So when we think about end behavior, we really want to focus on the highest degree term. We really want to focus on this term right over here, because as x becomes very, very, very positive, this term is going to dominate. And as x becomes very, very, very negative, this term is going to dominate. And so this term is really going to describe what the end behavior is. And we can even think about the end behavior here. We have a even exponent, so it's going to have behavior like x squared, which is just another way of saying that as x gets positive, the function is going to get positive, very positive. And as x becomes very negative, the function is going to become very positive because it's an even exponent. And the fact that there's a negative coefficient in front of this highest degree x term, this tells us it's going to be similar to the shape of negative x squared. It's going to be downward opening if you were to think about its end behavior. So which form of the function is most useful? Well, definitely D, the expanded out version. So I'll go with D. Select the equation below its similar end behavior to f of x. Well, we already talked about it. It's an even exponent, or it's an even degree, we could say, and then we have a negative out in front of it. So it's going to have similar end behavior to y is equal to negative x squared. And then they say which form of f of x is most useful for finding zeros? Well, when we're finding zeros, we're trying to find the x values that would make the function equal to 0. And this first form right over here, where we're all factored out, that's the most useful for finding zeros. We know that if we wanted to set this whole thing to be equal to 0, we said, hey, when does this equal 0? That means that one of these expressions, at least one of these expressions, need to be equal 0. We can independently set them equal to 0 and then solve for x. So this would be 0 when x is equal to 3, x is equal to 2, x is negative 1, and x is negative 5. So A is definitely the most useful for finding zeros.